So here's our first example of an optimization problem. This was from the actual multiple choice test in 1998. The maximum acceleration attained on the interval 0 to 3 by a particle that's moving at a velocity that's given here is. So we want maximum acceleration. So if you want to think about those steps that we wrote down, in case they're helpful, I use all those steps. I don't always typically number them out, but they're part of every optimization problem. So let's think about this. Which quantity are we supposed to optimize? So I read this and I see maximum acceleration. So that tells me I want to maximize the acceleration. Step 2, can I write a function for that quantity, acceleration? Well, yes, I can. I know how to find acceleration when I've been given velocity. And velocity is right there. Step 3, we're going to need critical points of acceleration. That means we're going to need places where the derivative of acceleration, a prime, is equal to 0 or is undefined. Once we have that function, that derivative, a prime, once we have the derivative of the function we want to optimize, we're going to set it equal to 0 and solve. We're also going to try to find out any t values at which a prime is undefined. So I'm going to write up a couple of those steps just so that we remember what we've done so far. All right, so question 1, what quantity do I want to optimize? I want to optimize acceleration, and specifically I want the maximum. And number 2, can I write an expression for acceleration? I can, in fact. Here's velocity. Oh, I'm having a little trouble reading that. That says t cubed minus 3t squared plus 12t plus 4. I'm going to take the derivative to get 3t squared plus, minus 6t plus 12. A prime of t. So step 3 is I need the derivative of that function I wanted to optimize. The derivative of a, notice a is polynomial, so this is no big deal. That's 6t minus 6. So 6t minus 6 is linear. There is no place where a prime is going to be undefined. So the only critical points for acceleration are places where a prime equals 0. And a prime is going to equal 0 at t equals 1. All right, so here I go. I have one critical point. It's at t equals 1. Step 5 says to make a table of values. My inputs are going to be any critical values and any endpoints, and my outputs are going to be that original function I want to optimize. Remember, that's what I said in the last video, is if I had a list of all the acceleration values, I would just pick the biggest one. So what I'm doing is essentially making a list of all the possible interesting acceleration values, and I'm going to pick the biggest one. So here's my table. My inputs are times, my outputs are accelerations. The input values that go in my list are endpoints, which were 0 and 3, and any critical points, which we said were 1. Now I'm going to find the acceleration at each of those values. So acceleration, here's my acceleration function. Don't go plugging into something else. But my acceleration at time 0 is 12. My acceleration at time 1 is 3 times 1 squared is 3, minus 6 is negative 3, plus 12 is 9. And my acceleration at time 3 is 3 times 9 is 27, minus 18 is 9, plus 12 is 21. So here is a list, not of every single acceleration value, but of all the possible acceleration values that might give me the maximum. I'm going to look through the list. I see that the largest acceleration value in the list occurs when time equals 3. I'm going to go back here and make sure I read this through and say the maximum acceleration attained. Because sometimes they'll ask the problem in a way that asks for the input value, but here they've asked for an acceleration, which is an output value, is, look at that, 21. Let's just make sure I got all the rest of those steps. Step 4 was to find the critical points. Step 5 was to make a table with all those critical points and endpoints as the inputs and the accelerations as the outputs. Number 6 was to Oh, that was to fill in the acceleration column. And number 7 was to pick, in this case I was looking for the maximum value from the output column, and double check the original problem to find out if I wanted the input there or the output. 21 is the maximum acceleration, time t equals 3 is when or where that maximum occurs. Alright, so we're going to try it again with a slightly more interesting problem, slightly more complicated problem. Yeah, that's probably true. So now I've been told y equals 2x minus 8. What is the minimum value of the product x times y? So I'm going to try the steps. Can I identify what, well, number 1, can I tell this is an optimization problem? This is about as obvious as they can get. They've used this word minimum value. They will sometimes use maximize or minimize, and those are like as specific as they can get. This is definitely an optimization problem. So what quantity is it that I want to optimize? Well, it's this product, x times y, that I am trying to minimize. Okay, step 2, can I write a function, an expression for that product, here's the catch, that contains only one variable. So I'm going to have a slight problem, which is, it's pretty obvious how to compute x times y. I take x and multiply it by y, but that has 2 different variables, and I've been told I can only use one variable. So here's my saving grace here, is I've been told that y equals 2x minus 8. So in my product x times y, I'm going to replace y with the quantity 2x minus 8. I'm going to write up my first 2 steps. Alright, here's what I have so far. I want to minimize the product of x and y, so I wrote this, I just called it p for product. I made a little function of x. It's actually a function of x and a y when I start, but I want it to be a function of x. So I called p of x, I said it was equal to xy, but then I said, I can replace y with 2x minus 8. So here's my function, p of x. I want to minimize it. What am I going to have to do? I'm going to have to choose those points that go in my table. We sometimes call them candidates. So candidates for the location of the absolute minimum of this p function are endpoints. I don't happen to have any endpoints here, and any critical points. Well, I find critical points by any critical points of p by finding p prime and finding out where p prime might be equal to 0, where it might be undefined. So p prime, you might choose to distribute that x. So this just becomes 2x squared minus 8x. And then it's quite easy to take the derivative, or you could go through the process of using the product rule. Either way is fine. So I just wrote out here, you can see I multiplied out that polynomial, and I get p is equal to 2x squared minus 8x. So when it's time to find p prime, I get 4x minus 8. Alright, so now that I have my first derivative, p prime of x, I can tell that p prime is always defined. It's just linear, so the question of is it ever undefined? No, p prime is never undefined. So my only critical points are going to come from where p prime equals 0, so I'm going to set 0 equal to 4x minus 8. I'm going to solve that. I get x equals 2. So that was step 4. I now have a critical point. I have one critical point, x equals 2. And step 5, I'm going to make that table. So here we go. The input values, in this case the inputs were x's. We said that an important x value to put here is 2. I'm also supposed to put any endpoints. Well, I don't actually have any other endpoints described by this scenario. So that's a good sign. There's really only one thing, well, 2 things left to do. Was it step 5 that says I should find the... Oh, so step 5 is to put the table and the x values in, the input values. Step 6 is to fill in the output values that go with those inputs. So here's a place we don't want to make a mistake. We know the minimum value of this original product function happens when x equals 2. Can we actually find that product? Well, go back to your original product function, where this version works too, right? Well, I guess you don't know why, so you're going to have to use that second version. So when x is 2, p of 2 is going to be 2 times 2 squared minus 8, which is Oh, okay, I just figured it out. Thank you. So P of 2 is going to be 2 times 2 squared minus 8 times 2. There we go. 2 times 2 squared, so that's 4 times 2 is 8, minus 8 times 2 is 16, negative 8. So that's what I get for the product, negative 8. You could go through this process here of checking that you're not making a big error. Since we only found one critical point, maybe somebody's trying to trick you, and that's really the location of a relative like a maximum of the function. But I think you will agree that if you have already gotten this far with your p function, you can tell that it's going to be a parabola that opens up. There's a leading coefficient that's positive. So the idea that it has a minimum makes sense. So here is the only line that ended up in your table. That's pretty cool. Don't make this common error, because look here. Yep, 2 is an answer choice. You have to be very careful at the end. We've picked the right row from our table. Don't get it wrong, it was the only row, right? But we have to make sure we understand from the original problem. Are they asking for the minimum value of the, in this case, product, or are they asking for the place where it occurs? They're asking for the minimum value, in this case our answer, negative 8.